Even though this set of problems is called gas calculations with mixtures, and we will be using Dalton's law, it's important to recognize we're still just focusing on the main gas laws, P equals nRT, and the variations on that we can use with Boyle's or Charles or Gay-Lussac's as well, and recognizing when do I need to treat my mixture as if it's all one thing, and when do I need to separate it out. So here we're talking about helium and oxygen. Initially, we're going to treat them separately. I've got a certain volume of helium at a certain pressure, and that needs to go into my smaller container. Well, for this, the helium acts independently of the oxygen acts independently of the helium. So when I take my helium and put it into that 5-liter container, its pressure goes up a lot. It is about 10 times, 9 times smaller of a container, so 9 times more pressure and collisions. So the pressure that comes just from the helium is 9.2 atmospheres. The oxygen goes from 12 down to 5, so we're cutting it in half or a little bit more than that, which is why the pressure goes up to about 2.4 atmospheres. So that's the pressure of each. The pressure of helium doesn't change the pressure of oxygen and vice versa. There's a question I've used on quizzes and free response previously, very similar to this, where people definitely get confused and try to think about combining or doing extra things with moles and PV equals nRT that isn't necessary. You can do more work to this and think maybe what are the total moles in here, but treating them as separate is probably the easiest way. But then once we recognize that there's 9 atmospheres of pressure from the collisions of helium, just over 2 atmospheres of pressure from the collisions of oxygen, well, both of those are banging around in that 5-liter container, which is where we have that total pressure of 11.6 atmospheres. So we kind of treat them as separate, but then recognize that when they're together, they interact, they probably bounce off of one another, but they don't necessarily change the pressure of the other. On our next one, we're looking at a collection over water. So this happens anytime we're kind of like creating a gas and bubbling it up through water to try to get the purest sample possible. So it will always have this kind of flow or look to it. And sometimes on AP free response, it's broken into multiple parts. And sometimes it's all at once and just worth more points. So they ask a few questions here, but that total pressure we recognize is the pressure from the gas we created, the oxygen, and the pressure from the small amount of water that evaporated. It would have to tell you the pressure of the water vapor. That's not something we can know off the top of our heads or calculate without enough information. So that 754 total pressure, 21 torr of that comes from the water, which means 733 comes from oxygen. In one recent example of this, we had this to start with, but they gave the pressures in 2 different units. One was atmosphere, one was torr. So there was that extra step to make sure that you knew they have to be in the same unit before we add, subtract, or do any calculations with them. So then that is the pressure of just the oxygen. We're now ready to use PV equals nRT with just the oxygen. Plug in the pressure, plug in the volume, and solve for how many moles. And in this case, I kept the 733 in torr using the R value that corresponds to torr. So you can choose to do that, or you can change to atmospheres. Probably in first year chem, we said it had to be atmospheres. You have to use this R, but we now understand a little bit better that R is just a constant necessary to cancel our other units. So we can choose whichever R matches with the unit that we're already in. That allows me to get my small number of moles. So with that, I've got a very small volume. If I had a full mole, remember it'd be over 20 liters. So by having less than 1 liter, it makes sense I don't have very many moles. So then here, and I wrote it incorrectly, or I typed it incorrectly, but I think I did the math correctly. We've got our moles of oxygen, 2 to 3 mole ratio of reactant to product, and then adding up the molar mass gets me my mass of KClO3. If I ended up doing the math wrong, send me a comment, let me know in class, but I think I put it in my calculator right to get the mass there. This one would be hard to do in your head, but a great free response type question. Make sure that you're thinking about and showing that mole ratio. That's very important. The last one here is just kind of practicing mole fraction. Mole fraction is technically a unit of concentration, but we don't use it for a lot of different things. It is most useful in its connection to Dalton's law, where we're looking at a total pressure and a partial pressure of a specific gas. So the mole fraction can be multiplied by the total pressure to get a partial pressure, or if I've got the partial pressure and total pressure, that allows me to get my mole fraction. It's basically just a percent that we keep in decimal form, which is weird because we call it a fraction, but we keep it in decimal form. There's no unit because the units have canceled on this. Just thinking about what percentage of my sample or my pressure in this case is coming from a specific gas. So there's 156 torr that comes from oxygen. The total pressure is 753. So just what percentage that? Oxygen's about 20 to 21% oxygen, which in terms of a mole ratio is 0.21. So then we might use that later, or we might use that to find the mole ratio or the mole fraction of another gas. I just wanted to have one simple one showing and talking about mole fraction. It applies here. There are other values that we use and think about with this, but not things that we necessarily do in the gas unit or even in AP Chem. So mole fraction does have other uses, but in terms of chemistry or in terms of AP chemistry, its biggest connection is with Dalton's law.